Hi, and welcome again to the class Electrical Systems in Agricultural and Biosystems Engineering. This is lecture number 4, and we're going to tackle uh, we're going to discuss or solve for problems involving uh, RLC circuits, right? So let's proceed with that, and we're actually going to deal with 3 problems. Let's start with the first one, and it's going to be on or involving an inductor. So the problem instructs us to solve for the inductive reactance and the current. So this are I, and the inductive reactance is X sub L, right? Sorry. So this is X sub L, and this is X sub L, and this is the current. Okay. Let's try to solve this, and well, in the manner of engineering, right? So let's try to draw the diagram first, right? So given, oh, sorry. All right, so we have a given what's wrong with this? What's happening? All right, so we have the given, and holding on to something. Given is that we have a just draw the setup, right? So we have a 120 volt, 60 hertz voltage source in one end, and the other is connected to a 0.3 Henry inductor. So we are going to find A, inductive reactance X sub L, and B, the current through the inductor I. That's I sub L. Okay. These are very direct. The equations have been already discussed in class. We're going to make use of 2 equations, and the idea is for us to first solve the inductive reactance, because and logically we have to find the equivalent resistance, that is the inductive reactance of the inductor, okay, the circuit. So solutions. Okay, so A, we have the formula is it's X sub L equals 2 pi FL. So the source of the voltage is already given of its frequency. This is the frequency, okay, and this is the inductance. Again, it's a plug and solve problem, so you directly just substitute or plug in the values for the F and the L. Okay, so F is 60 hertz, and you have your inductance of 0.3 Henry. and you'll be able to solve 113 ohms. Right, so once that's done, you can now solve. You're going to treat this as a resistor. Okay, so eventually you're going to make use of the voltage current law. Okay, so you have your voltage equation equals to IR, and I is V over R. Okay, eventually just going to plug in the values. You have your 120 volt source, and okay, so 120 volts divided by the let's just substitute the R for the with the hexabel so that it's clear that they're equal. Right, so V is 120 volts, and you have your resistance at 113, or reactance at 113 ohms, and I is equal to 1.1 amperes. Right, so that's our solution for the problem. And we go to the next problem. We are going to talk about another circuit. Okay, so in this problem, we have a transistor radio consisting of a 20 millihenry coil of 8 ohms resistance. So instead of well, instead of having the frequency across the resistor or the inductor, we have the equivalent resistance provided. Now there is a variable capacitor. It's the design of transistor radios. There is a variable capacitor, and varying the capacitor would change the uh, the 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 it enables the radio, okay, to access different wavelengths of signals, okay, and that's the idea for your transistor radio, so it is able to receive different amplitude modulation and frequency modulation um, um, signals, okay, or radio waves, so that there are different radio stations, okay, in the transistor radio. So what's being asked are the capacitance needed to tune the radio station to a certain hertz, okay, frequency. It's 920 kilohertz. And the second information required is the current in the antenna circuit if the radio wave received at the antenna produces an AC signal of 2.0 times 10 to the negative 5 volts, okay? And then lastly is the AC voltage across the coil. Right, so we will now, I think everything, all the given is, all of the given are provided for. Okay, so let's proceed solving the problem. Okay, so let's try to first identify the given. So given, we have an RLC series. So it's a series circuit with R equals 8 ohms. The L is 20 times 10 to the negative 3 Henry. okay, because it's milli or millihenry, right? But to simplify the solution later, we uh, we want to express that in scientific notation already. Okay, so C is variable, and that enables the transistor radio to work. We're trying to find the A, the C needed to tune in the radio, the C value to tune in to 920 kilohertz. Okay, let's once again put that times 10 to the 3 hertz, okay, or kilohertz. B, okay, the I in the antenna circuit, if V equals 2.0 times 10 to the negative 5 volts, or what's the value for this one? It's actually, yeah, it's already given, so let's just set it as that. Now C is the voltage, the AC voltage across the wire. I think these are very direct. It's just that we have to understand what is really being asked for. Let's go proceed with the solutions. Okay. Right. So we know the formula for our C as 1 over 2 pi FL. Now we have to take note that the frequency, okay, the frequency that we want to achieve is, okay, 920, right? So we use the formula, okay. Oh, sorry, this is for X sub C. So the formula for C is actually 2 pi, I recall, 2 pi F sub 0 squared over L times L, okay. So this is 1 over 4 times pi squared times F sub 0 is 920 kilohertz. So it's 9.20 times 10 to the 5 hertz. And then we have the Henry. So this is squared. And we have Henry value for the inductor. It's 20 times 10 the negative 3 Henry, right? So it's good that we can already solve directly for the capacitance in farad. So we solve this, right? How big is this? Let's try to solve. Okay. My calculator is 4 times pi squared. Okay, 9.2 squared times 20 times 10 to the negative 3. All right, so this is equivalent to 1.5. Sorry, 1.5 times 10 to the negative 12 farad, or it's equal to 1.5 picofarad. Right, letter B is the okay, let's just try to understand letter B better. Okay, so the current in the antenna, if V equals 2.0 times 10 to the -5 voltage, okay, so this happens if we have the system at resonance. So when we have at resonance, it means that Z equals to R. So at resonance, recall that Z equals to R, thus, or since, okay, since or thus we have, or since we have X sub C equals X sub L, so they'll just cancel, okay? Remember the equation Z equals square root of R squared minus R. Okay, sorry, this is L, X sub L minus X sub C squared. So this gets cancels, okay? And we are left with the equality Z equals R. Now, okay, so since we have that, the voltage equation will be, or the current will become just I equals V over R. And we have that, I equals 2.0 times 10 to the -5 voltage, because that is our target voltage, or that's the output voltage that's required. So we divide it by 8 ohms, which is the resistance of the coil, okay, the coil. So let's give it, okay. So we get I equals 2.0. So 2.0 divided by 8 is actually 2.5, but we just have to move the it's actually 0.25. So we move the scientific the power. Okay, so it's 2.5. It's actually 0.20. Okay, 2.5 times 10 to the -6 amperes, or yes, 2.5 times 10 to the -6 amperes. So we now move to or this could be, we can say that this is 2,500 milli. Oh, sorry, to 0.0025 milliamperes. Okay, so we get C. Okay, C is the, what we're finding with C. We're looking for the voltage across the coil. Now, the coil is expressed in terms of the Henry, because that is the inductance. So we solve for V using the equivalent resistance, okay, which is X sub L. And X sub L is equal to 2 pi FL. So I times 2 pi FL, okay, it's just simply as 2 pi f Li, and we have 2 pi times f, which is 2 point, sorry, it's the frequency is 920, right? So 9.2 times 10 to the 5 hertz times the inductance, which is 20 times 10 to the negative 3 Henry times the I, which is 2.5 times 10 to the negative 6 amperes, which we have just solved from over here, right? So we can now get for the voltage across the inductor by simply solving for this one. So this is 9.2 divided by 20 times 20 times 2.5 times 10 to the negative 6 times 2 times pi. Okay, times 2 times pi. So it's 0.8289, 0.289 volts. Or you can actually round it up to 0.3 volts. Right, so those are the examples. In the next problem, okay, we have another problem. Our next problem involves now a coil, okay, that has an inductance of 46 millihenry and a resistance of 8 ohms. Now the inductance, there's a scenario if it draws 5 amperes of current from a 100 volt RMS 60 hertz power supply. The following are to be determined. First, the voltage across the voltages across the resistor and inductor, the real power, reactive power, and apparent power. And lastly, the equivalent capacitor to increase the power factor to 0.95. Okay. Okay, let's proceed with the solution. We are given this problem, right? So given, we have the given an RL circuit with L equals 4 to 6 times 10 to the negative 3 Henry, and R equals 8 ohms connected to a VRMS 100 volt power supply with F equals 60 hertz. We're to find the VR and VL, the P real, P reactive, and P apparent. And lastly, C. Okay, C, which is the C, the capacitor C value to raise or for PF power factor value, we identify it with a prime. So to differentiate with the actual power factor that we get to solve initially, the value of 0.95. All right, solutions. I think letter A are directly solvable. So we have VR equals IR, and we have 5 amperes, okay, times yeah, it's given, okay, 5 amperes, and we just multiply that with 10 ohms. All right, so we have here 8 ohms. Apologies for that. I thought it was 10. So it's 8 ohms, and we get V sub R equals 40 ohms, 40 volts. Okay, and VL now is simply I times X sub L, and uh, adjusting the formula to so that we can solve using the given. So 2 pi times 2 pi FL, and we get, okay, 2 pi, okay, this is pi amperes times 2 times pi times the frequency, which is 60 hertz, and we have 46 times 10 to the negative 3 Henry. So solving for the BL, we get 5 times 10, that's 10 times 10 to the, actually 2 point, so this is actually what? We get the value 86.7 amperes. Voltage, sorry, it's volts. 86.7 volts. Okay, so we have now solved for A. We are going to solve for B. B is simply the real, reactive, and apparent powers of the system. So the P real, sorry, that's real, equals VI cosine theta. Okay, now that sorry, okay, so we have to solve for the theta first. Now theta is again tangent negative, or the inverse of the tangent of 86.7 over 50. Okay, and we get what? 6.7 divided by 50, shift tangent. Okay, apologies, this is actually 40, so we just have 40 over here. Okay, so we have 86.7 divided by 40. This is 65, okay? 65 degrees. Right, so we can now solve for the period, and it's V is uh, V is actually 100 volts times 5 amperes. 100 volts times 5 amperes times cosine of 65 degrees. So we get the value of 100 volts times 5 times cosine 65 times 5 times 100. Okay, so wait, sorry. Cosine 65 times 5 times 100. So it's 211. Okay, 211. The period is 211 watts. Okay. So we have now the P reactive. The P reactive is VI sine theta. Okay, so P reactive is equal to 100 volts times 5 amperes times sine 65 degrees. Okay, so we have this value as, okay, sine times 5 times 100, which is 453. Okay, the P reactive is 453 watts. Okay, we're now solving for the P apparent. The P apparent is equal to VI, which is 100 volts times 5 amperes equals 500 VA. Just to separate or distinguish the value of the P apparent with the reactive and real powers. Okay, we use the notation VA for the unit. All right, so we are now looking for the C, or the capacitor value in farad, to raise the power factor to 0.95. Take note that um, the 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 uh, the value of the power factor is exactly uh, the the value of the phase angle when converted to decimal. Okay, so we can say that we want to raise the theta to a value that is the cosine of negative 1 of 95, or 0.95. This is our 95%. Okay, and we have 18, this as 18.2 degrees. That's a very um, uh, high value actually of power factor. So we want to establish a a value, okay, for your new P reactive, because we want to reduce that. Okay, the reactive is what we want to reduce. So the P reactive would need to become what? We have to have a P reactive value of P real times the tangent of tangent theta. Okay, so this is 200, but this is 211, right? 211 watts. 211 watts times tangent of 18.2 degrees. We get the value 82. Is it 82? Or let's see. Tangent 18.2, tangent 18.2 times 211, we get 69. Okay, this is 69 VAR. Okay, to solve now for the P net, the difference between your original reactive power and the new one, we simply subtract the P net. Okay, the P react net equals the P reactive prime minus the P reactive, which is the original. Sorry, we want to, so we use the reactive first. We put that first. So P reactive prime. Okay, so this becomes, oh, this is 453, right? 453 watts minus 69. Okay, and okay, we use the unit 53 VAR minus 82.2 VAR, and we get the value, oh sorry, this is 69 VAR, and we get the value 453 minus 69 is 384. Okay, 384 VAR, and we know that the P net, okay, this value for the P net is solely due to the capacitor. So we can now solve for the X sub C, which is X sub C equals V squared over P net. Okay, we have the X sub C equals VRL squared over the P net. Okay, so VRL is what? VRL equals VRL is, well, the V R squared plus V sub L squared, and these are equal, this is equal to 50 volts squared plus 86.7 volts squared. And we get what? We get, actually, we get the value, um, this is 40 volts. This is 40 volts. 40, this is 40 volts, and we get the VRL equals 40 squared, 86.7 squared plus, okay, so we get 95 point, we just round up 95 volts, and we can say that the P net, okay, since we got the P net, the P net, okay, this is just, okay, the P net is 384 VAR. Okay, so we can solve for the X, the value of the reactance of the capacitor as 95 volts over 3, that's what, 384 VAR, and we get the value. Okay, so this is squared. Okay, this is squared. Yeah, it's squared. So we get the value 95 squared divided by 384. Okay, so we get 23.5 ohms. Okay, ohms. Now the C, we can solve using our equation 1 over 2 pi F X sub C. Okay, remember that this is the same formula when solving for the reactants. Okay, and this becomes what? Okay, this becomes 1 over 2 pi times 60 hertz times 23.5 ohms, and we get the value of what? Okay, 1 divided by 2 divided by shift pi. Where's the pi? Yeah, there it is. Divided by 60 hertz. Okay, and divided by 28.5. So it's 9.3. Okay. Oh, sorry, it's 23.5. Okay, sorry, apologies. We get 23.5 as the value of our the reactance of the capacitor. So 1 divided by 2 divided by 60 divided by 3.5. Okay. So it's 1.12, or yes, 1.12. Okay, 1.12, 0.01, or yeah, 0.01 farad. So 1.13 times 10 to the negative 4 farad. That is the value of the capacitor, okay, that we have to add to the system to improve the power factor of the system. Okay, so I'll be meeting you next time with our next topic, which is on energy or in power and energy. So we deal with the power generation sources, okay, that are needed to generate electricity. Thank you for listening, and um, I'll be seeing you until now.